Welcome to Lecture 2.1, Anonymous Functions for Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you will have an understanding of what functions are, what anonymous functions specifically are, how to write anonymous functions, how to determine appropriate uses for anonymous functions, and how to write an anonymous function for the vector dot product. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. To introduce a practical definition for functions, consider this question. What are the steps involved in determining the color of a rose? For us, as humans, this is likely as simple as visual observation of the color. But consider how a machine might identify a rose's color in the case that there is an unreasonably large pile of roses to sort. It might include the following steps. First, illuminate a rose under a white light. Then a sensor could measure the intensities of the reflected wavelengths, and then finally to convert the reflection spectrum into an RGB color code. If you are interested in how this works, the hyperlink on this page directs you to a relevant resource. These steps describe a human-agnostic approach to identifying a rose's color. With a well-defined algorithm, a machine can be designed that automatically applies these steps, which can be used in sorting a large pile of roses. And with such a machine, the person operating it no longer needs to consider every individual step. They can just turn on the machine. This is a mechanical analog of what would be considered a function in programming, perhaps given the name sort rows by color where the input is a rose. So, a function encapsulates a set of instructions that accomplish a very specific task. The purpose of a function is to make the broader program more modular, especially when an operation gets repeated many times. Functions make code easier to read, debug, and to maintain. And with that, what are anonymous functions specifically? Anonymous functions are one-line operations that can be called from anywhere within a script in which it is defined. It is used to extract a specific repeated piece of the script into a distinct unit within that script. The operation can then be executed anytime by accessing the function itself rather than rewriting the same code over and over again. The syntax for declaring an anonymous function is as follows. First comes the variable name in which it will be stored. Then an input can be specified in parentheses following the @ symbol, and if necessary, you can specify multiple input variables in this way. And finally, the function operation itself comes after. Remember, it can only be one line of code. For example, an anonymous function that returns the square root of the input raised to the 6th power would be written as follows. The name, for now, is just fancy function, and its only input is the variable x. And the operation is raising x to the 6th power and then taking the square root of that using the square root command. This stores the operation square root of x to the 6th power in the variable fancy function. Once it has been declared, the function operation can be accessed by calling the variable name just like any other variable. We have the function definition, again, and then we define a variable a to operate on, and if we pass a into the function, it returns the result b is equal to 8. So, what is a good application for anonymous functions? Well, in general, functions are recommended when an operation needs to be reused several times. And anonymous functions in particular are good for very short operations. And as we have seen, it is very simple to define one line of math that needs to be calculated repeatedly. This can help with avoiding mistakes by mistyping the operations if you choose not to write a function. The vector dot product is perfect for an anonymous function. The math for it is very simple. It's just one line of math where v1.v2 is equal to v1x times v2x plus v1y times v2y plus v1z times v2z. and that can be implemented with a short function that accepts two 1x3 vectors like those discussed in the previous lecture as inputs. We'll store it in a variable called the dot product and define the two inputs with the @ operator as v1 and v2. Then we multiply the x components of v1 and v2 by accessing the first element of each vector using the index 1 in parentheses. Then we add the product of the y components in the same manner but with index 2. And finally, we add the z components with index 3. With the function defined, it is possible now to solve for the dot product between any two vectors, crucially, without having to rewrite the code each time. The dot product anonymous function is first defined. Then let's define vector 1, vector 2, vector 3, and vector 4. And if we want, solving for the dot product between vectors 1 and 2 requires using just vectors 1 and 2 as the inputs to the anonymous function. And similarly, solving for the dot product between vectors 3 and 4 requires, again, using 3 and 4 as the inputs. Now, the results of both of these computations are as follows. The first dot product between vectors 1 and 2 equals 32, and the second between vectors 3 and 4 equals 266. Rather than replicating the code each time, it's better practice to write the code once in a function and then to use that multiple times instead. In summary, functions are powerful units that extract some operation and can be called multiple times with different inputs each time. Anonymous functions specifically are written in one line and can be called from anywhere within the same script. They are great for short operations like simple math. Anonymous functions are stored in a variable name and can accept input arguments which are specified with @ parentheses and the inputs contained within, followed by the function declaration itself. When to use an anonymous function comes down to when you have short repeated operations that are perfect for extracting into an anonymous function to make a more modular and therefore more maintainable program. And finally, the dot product makes a great example because the math is simple and it is a very common operation in engineering. The inputs are both 1x3 vectors which were covered in the previous lecture, and the function then calculates and returns the scalar output.